Hello guys. So this is Russell Guadalupe and I'm going to present some examples and exercises of series of constant terms and their convergence. So first, let's recall what we have learned from the lesson last time about series of constant terms. We say that an infinite series of real numbers is convergent with sum s if the sequence s of k from k equals 1 to infinity of partial sums where we define the k partial sum as the sum of the first k terms s of k converges to s. In this case, we write our sum as the sum of a sub n from 1 to infinity equal to s. We say that an infinite series is divergent if the sequence of partial sums diverges. So from the lesson that you have learned last time, you have learned two important series. The first one is the geometric series, which converges to a over 1 minus r for non-zero real numbers a and r whenever the absolute value of r is less than 1 and diverges otherwise. Another important series is the harmonic series, which is the sum of 1 to the n from 1 to infinity, which is divergent. So you also learn the following theorems here, which establishes the divergence and convergence of one series in relation to the other. So for number one, we see that if the series A sub n convergence, then so does any multiple of a series for non-zero number c. So in the convergence case, we have the following equality here. For the second, if two series A sub n and B sub n both converge, then the series with the n term A sub n plus B sub n converges with the sum equal to the sum of the original two series. If the series A sub n converges and the series B sub n diverges, then the series with n term A sub n plus B sub n diverges. And finally, if we have A sub n equals B sub n for all but a finite number of values of n, then the convergence or divergence of B sub n will depend on the convergence or the divergence of A sub n. Recall that if the series A sub n converges, then the limit of the n term A sub n as n goes to infinity equal to 0. Equivalently, we have the following contrapositive known as the divergence test, which states that if the limit of A sub n as n goes to positive infinity is non-zero, then the series A sub n is divergent. As a remark, if the limit of A sub n as n goes to positive infinity is 0, then the divergent test is inconclusive. So in this case, we have to apply other methods, such as by looking at the partial sums, to establish the convergence or divergence of the given series. So we're going to solve some examples here. So I encourage you to pause this video and try to solve as many problems as you can. Okay, so let's proceed. So let's now consider our first example. Let's determine whether the series, the sum of 3 to the n minus 1 all over 4 raised to n plus 1 from 1 to infinity converges or diverges. So first, let's write the given series as follows. We write 3n minus 1 as 3 to the n over 3 and 4n plus 4 raised to n plus 1 as 4 times 4 to the n. So the n term of the given series becomes 1 over 12 times 3/4 raised to n, and therefore our given series can be written as the sum of 1 over 12 times 3/4 raised to n from 1 to infinity. And this is a geometric series whose first term is 1 over 12 times 3/4 or 1 over 16 and common ratio 3/4. Because the absolute value of 3/4 is less than 1, the given geometric series is convergent with sum given as follows. So we have A equals 1 over 16 and R equals 3/4. So the sum in this case is A all over 1 minus R equals 1 over 16 all over 1 minus 3/4, which gives us the sum 1/4. Okay, for our next example, let's determine whether the series, the sum of n squared all over ln of n plus 1 from 2 to infinity converges or diverges. So as a first step of our solution, let's define f of x equals x squared all over ln of x plus 1 on 2 to infinity. Then we compute the limit of f of x as x goes to positive infinity, which gives us the limit of x squared all over ln of x plus 1. And as you can see, the limit of x squared tends to positive infinity, and the limit of ln of x plus 1 tends to positive infinity as well. So in this case, we have an indeterminate form of infinity over infinity. So in this case, we have to apply L'Hopital's rule, in which we differentiate both numerator and denominator as follows. So the numerator has derivative 2x and the denominator has derivative 1 over x plus 1. So in this case, applying LHR, we see that this limit is equal to the limit of 2x all over 1 over x plus 1 as x goes to positive infinity, which can be simplified to the limit of 2x times x plus 1 as x goes to positive infinity. And we can actually factor out a in this way, we have the limit of 2x squared times 1 plus 1 over x as x goes to positive infinity. And as you can see here, x squared grows very large as x grows very large as well, and 1 over x will tend to 0 when x is sufficiently large. In this case, we have the limit of the uh, expression in enclosed parentheses is 1, while the limit of 2x squared is positive infinity. So therefore, the limit of f of x as x goes to positive infinity is positive infinity. So in this case, the limit of our n term, which is n squared all over ln of ln n plus 1 as n goes to positive infinity is positive infinity. And therefore, by divergence test, the given series is divergent. Okay, so let's now proceed to another example. Let's determine whether the series, the sum of quantity 1 over 2n plus 1 over 2 raised to n from 1 to infinity converges or diverges. So first, let's write the given series as the sum of the series 1 over 2n from n equals 1 to infinity and the sum of 1 over 2 raised to n from n equals 1 to infinity. Observe that the first series can be written as 1/2 times the sum of 1 over n from 1 to infinity. And this first series here is divergent because it contains a multiple of the harmonic series 1 over n, the sum of 1 over n from 1 to infinity, which is known to be divergent. And the second series, the sum of 1 over 2 to the n from n equals 1 to infinity is convergent because this is a geometric series whose common ratio is 1/2, which is less than 1. So we have a convergence series and a convergence series and a divergent series, and we are taking the sum of this series. So therefore, by our theorem, the given series diverges. Let's now proceed to our next example. Let's determine whether the series, the sum of 3 to the n minus the n power of -2 all over 6 to the n from 1 to infinity converges or diverges. So first, let's write the given series as the sum of 3 to the n over 6 to the n from 1 to infinity minus the sum of -2 quantity raised to n over 6 to the n from 1 to infinity. So the first series can be written as the sum of 1/2 raised to n from n equals 1 to infinity. And then the second series can be written as the sum of negative 1/3 quantity raised to n from n equals 1 to infinity. Note that the first series, which is the sum of 1/2 to the n from n equals 1 to infinity, is convergent because this is a geometric series with first term and common ratio both equal to 1/2, and 1/2 is less than 1. And the second series, which is the sum of negative 1/3 to the n from n equals 1 to infinity, is convergent as well because, again, this is a geometric series with first term and common ratio both equal to negative 1/3. And therefore, the absolute value of negative 1/3 is less than 1. So as you can see, we have a series which can be written as a difference of two convergent series. So therefore, by our theorem, the series converges to the following. So we have the given series here, and again, this is equal to the difference of the two convergent series. So the first series here has sum equal to 1/2 all over 1 minus 1/2. The reason is that the first series is a geometric one with first term a equals 1/2 and common ratio r equals 1/2. So the sum is given in this way, 1/2 all over 1 minus 1/2. And then the second series is convergent as well because it's a geometric series with first term a equals negative 1/3 and r equals negative 1/3. So therefore, the second series converges to negative 1/3 all over 1 minus negative 1/3. So therefore, computing this expression here gives us the sum of the given series, which is equal to 1 plus 1/4 or 5/4. So let's now consider the next harder example here. Let's find whether the series given by the sum of 1 over 16n squared minus 8n minus 3 from 1 to infinity converges or diverges. So observe that if we apply the divergences to the series, we will yield an inconclusive result as the limit of the n term, 1 over 16n squared minus 8n minus 3, from as n goes large, which can be written in this way. We actually have to factor out n squared on the denominator, giving the limit of 1 all over n squared times 16 minus 8 to the n, 8 over n minus 3 over n squared as n goes to infinity. And as you can see, the expression inside the parentheses approaches to 16, while n squared grows large as n grows large. So therefore, our fraction here will be smaller and smaller and closer to 0. So therefore, the limit of the n term is 0. So in this case, we study for the convergence or divergence of the series by using partial sums instead. So our goal here is to find a closed form formula for the partial sum of this given series. So first, let's write for some constants a and b. So as you can see, we can actually factor out the denominator of our n term, 16n squared minus 8n minus 3 as follows. We have 4n minus 3 times 4n plus 1. So in this case, our a sub n here can be written as 1 over 4n minus 3 times 4n plus 1. And as you can see, we have two linear factors involved. So this can be written as the sum of a over 4n minus 3 plus b over 4n minus 1 for some constants a and b. And then multiplying both sides by 16n squared minus 8n minus 3 yields the resulting equality. 1 equals a times 4n plus 1 plus b times 4n minus 3. If we set n equals 3/4, then the second summand b times 4n minus 3 will cancel out, giving 1 equal to a times 4 times 3/4 plus 1, or equal to 1 equal to 4a, which gives us a equals 1/4. On the other hand, if we set n equals negative 1/4, then the first summand a times 4n plus 1 will cancel out, which yields 1 equals b times negative 1 minus 3, or b, 1 equals negative 4b, which gives us b equals negative 1/4. So if we set these two values of n, that will make one of the summands equal to 0, we will get the value of the other variable. So this gives us the ordered pair AB equals 1/4 negative 1/4. Thus, we can now write our n term as 1/4 all over 4n minus 3 minus 1/4 all over 4n plus 1. And then we can factor out 1/4 as follows. So therefore, our n term here is equal to 1/4 times quantity 1 over 4n minus 3 minus 1 over 4n plus 1. And we will use this decomposition to find explicitly the closed form formula for the cake partial sum S of k. Let's now continue our solution. So for each integer k greater than or equal to 1, we compute the cake partial sum, which is equal to the sum of the first k terms of our series. And therefore, we have to use the partial fraction decomposition of 1 over 16n squared minus 8n minus 3, wherein we put 1/4 outside of the sum, and thereby considering the sum of this expression from n equals 1 to k. If we expand this sum fully, we will get this. And observe that if n equals 1, the first term here will be 1 minus 1/5. If n is equal to 2, we have 1/5 minus 1/9, and so on until we reach corresponding term for n equals k, which is 1 over 4k minus 3 minus 1 over 4k plus 1. And as you may notice, some of the terms will cancel out. For instance, negative 1/5 plus 1/5 is 0, negative 1/9 plus 1 equals 0, and so on and so forth. So this means that we have obtained a telescoping sum wherein the only terms left are 1 and negative 4k plus 1. So in this case, S of k is equal to 1/4 times 1 minus 1 over 4k plus 1, which can be written as 1/4 minus 1 over 4 times 4k plus 1. And this is the closed form formula for the cake partial sum S of k. So that if we take the limit of S of k as k grows large, this yields the limit of 1/4 minus 1 over 4 times 4k plus 1 as k grows large. And as you can see, if k grows large, so does the denominator 4 times 4k plus 1. So in this case, 1 over 4 times 4k plus 1 will tend to 0 as k grows large. So therefore, the limit of S of k as k grows large is 1/4. So we conclude that the series is convergent with sum 1/4. Let's now consider our next example here. Let's determine whether the given series, the sum of n over 4 to the n from 1 to infinity, converges or diverges. So again, just like in the previous example, let's define f of x as x over 4 to the x on 1 to infinity. Then we try to find the limit of f of x as x goes to positive infinity. In this case, this is equal to the limit of x over 4 to the x as x grows large. And again, the numerator goes to positive infinity. The denominator also goes to positive infinity as well, whenever x grows sufficiently large. So in this case, we have to apply the L'Hopital's rule. This means that we have to differentiate both numerator and denominator. So for the numerator, we have the derivative of 1. For the denominator, we have the derivative of 4 to the x ln 4. And as you can see, the limit of f of x as x goes large is equal to the limit of 1 over 4 to the x ln 4 as x goes large. And this will make 4 to the x ln 4 bigger. So therefore, this fraction goes to 0. And this implies that the limit of n over 4 to the n as n goes to infinity is 0 as well. So we will use this limit later. And by divergence test, we have an inconclusive result. So again, just like in the previous example, we have to consider instead the partial sums to establish the convergence or divergence of the series. So for each integer k greater than or equal to 1, we write the k partial sum s of k to be the sum of the first k terms of our series. So in this case, we have s of k is equal to 1/4 plus 2 over 4 squared is 3 over 4 cubed, and so on until k over 4 to the k. And then our next step that we will do is we multiply s of k by 1/4, and we have to rewrite our sum in this way so as to match the coefficients of 1/4. So in this case, we have 1/4 s to the k is equal to 1 over 4 squared plus 2 over 4 cubed, and so on until k minus 1 over 4 to the k plus k over 4 to the k plus 1. And then we have to subtract the second summation, or the second sum rather, from the first one. So if we do that, we have 3/4 s of k is equal to 1/4 plus 1 over 4 squared plus 1 over 4 cubed, and so on, plus 1 over 4 to the k minus k over 4 to the k plus 1. And observe that the first k terms here then gives or form a finite geometric series. So the sum of this finite geometric series is given by 1/4 over times quantity 1 minus 1 over 4k plus 1 all over 1 minus 1/4, because the first term of our finite geometric series is 1/4, and the common ratio here is 1/4 as well. So we have this sum. This is the sum of the first k terms of a finite geometric series, and then we subtract it with k over 4 raised to k plus 1. Then we have to simplify this. So s of k is equal to 4/9 times quantity 1 minus 1 raised to 4k plus 1 minus k raised to 4k over 4k plus 1 raised to k plus 1. So in this case, so this is the closed form for s of k, and then we now take the limit. The limit of s of k as a goes large is equal to the limit of 4/9 times quantity 1 minus 1 all over 4 raised to k plus 1 minus k all over 4 raised to k plus 1 as k goes large, which can be written in this way. So you have 4/9 times the limit of 1 minus 1 over 4 raised to k plus 1 as k goes large minus 1/4. Take note that we have to factor out 1/4 times the limit of k over 4 to the k as a goes large. And again, as k grows large, 1 over 4 raised to k plus 1 will tend to 0. So the value of the first limit here is 1, while the value of the second limit is 0. Okay? This second limit comes from applying L'Hopital's rule from the previous slide. So therefore, our limit of s of k as a goes large is 4 over 9. So hence, we conclude that the series is convergent with sum 4 over 9. And finally, let's now deal with our last example. We are given a sub n equals 2n cubed minus t all over 5n cubed minus 2n. Let's determine whether the sequence a sub n from 1 to infinity converges or diverges. So since the limit of a sub n is equal to the limit of 2n cubed minus t all over 5n cubed minus 2n as n grows large, and then as you can see, n cubed grows very faster than the other terms involved here. So we have to divide both numerator and denominator by n cubed, which gives us the limit of 2 minus 3 over n cubed all over 5 minus 2 over n squared as n grows large. And as you can see, 1 over n cubed, 3 over n cubed, and 2 over n squared will go to 0 as n goes to infinity. So therefore, the limit of a sub n as n goes to infinity is 2/5. So in this case, we conclude that the sequence a sub n from 1 to infinity converges to 2/5. Alternatively, we can actually use L'Hopital's theorem to find the value of this limit, and you will get the same answer of 2/5. Our next question is we need to determine whether the given series, the sum of a sub n from 1 to infinity, converges or diverges. So from the previous item, we have the limit of a sub n as n grows large is 2p, which is non-zero. So therefore, by the divergence test, we conclude that the series a sub n from n equals 1 to infinity diverges. Okay, uh, okay, so I hope you learned something about establishing the convergence or divergence of some selected series here. So I will leave to you the following exercises for you to solve during your free time. So if there are no more questions, clarifications, uh, I hope that you learned so much about uh, a series of constant terms and establishing their convergence using uh, partial sums or divergence tests. So thank you for listening.